All right, the fun continues. I'm going to look at operations on complex numbers in polar form now. So, lecture 33 of specialist maths, and what a great day for it. It's Pi Day, 14th of March, so it'd be rude not to make a maths video. Not that this really has much to do with pi, but still pretty cool. All right, some prior knowledge to understand operations on complex numbers would be the previous 3 videos where we introduced complex numbers. Then we looked at the modulus, conjugate, and division of complex numbers in what's called rectangular form or Cartesian form. And then we learned what polar form is. So then we did polar form of complex numbers. And what will be helpful for this video are these 2 previous videos as well, when we learned about proof by induction. And we also learned about the compound and double angle formulae, which was lecture 15. So the key concepts we'll cover in this video are addition and subtraction of complex numbers in polar form, multiplying a complex number in polar form by a positive or negative scalar, multiplication of complex numbers in polar form. So when you multiply 2 complex numbers together that are in polar form, we'll do a proof of that. Then we'll look at division of 2 complex numbers. We'll also do a proof of that. And then the proof of de Moivre's theorem using induction. I've never learned how to say this, so let me pause and find out how to actually say it. De Moivre's theorem using induction. So we'll look at that. Let's jump into it, see if we can make some sense of this stuff. So just as we're sort of singing the praises of polar form, we want to add, if we wanted to add 2 complex numbers in polar form, we actually can't do that very easily, and we need to convert back to polar form. So here's an example. I just noticed an error. I'm just going to fix that. Okay, the reason it said basic operations on vectors there is because I think of complex numbers as vectors in a lot of ways. So I must have just written that. But we're doing basic operations on complex numbers. And as I mentioned, when we're adding or subtracting complex numbers in polar form, we actually need to convert back to Cartesian form. So, and then add them by adding the real and imaginary parts. So here's just an example. I'll just talk through it. So if you've got 4 cis pi on 4, that's over here. So a radius of 4, the modulus is 4. Pi on 4 around, so that's 45 degrees. So that's there on our sort of polar Argand diagram. And then we're adding that to 5 cis 3 pi on 4. All right, so that must be on the 5th circle because there's a radius of 5. And 3 pi on 4, well, that's pi on 4, 2 pi on 4, 3 pi on 4 is over here. So convert it to Cartesian form. Well, if we just look at this first one, 4 cis pi on 4, we need to know a little bit about our exact values. Remember, cis is cos plus I sine theta, and theta in this case is pi on 4. The angle is pi on 4. Cos of pi on 4 is root 2 on 2. Sine of pi on 4 is also root 2 on 2. So when we convert this to Cartesian form, we get 2 root 2 plus 2 root 2 I. Okay, similarly, we do the same thing here. 5 cis 3 pi on 4 becomes this business. And yeah, we do the same thing and we get negative 5 root 2 on 2 plus I times 5 root 2 on 2. Okay. Yep, that makes sense. Cos is negative root 2 on 2 over here, and sine is positive root 2 on 2. All right, then you add the real and imaginary parts. So you take the real component of the first one and add it to the real component of the second one. And then you do the same thing with the imaginary components, and you'll get this. Okay, vectors, the reason again we sort of show it as vectors is this. We're basically adding these vectors. If you think about a vector from the origin to those things, what you can do is if we move that vector on top there, and then connect a new vector here to sort of show this point here is our resultant vector when we add those 2 complex numbers together. We get this pink one. And let's see, negative root 2 on 2 plus I times 9 root 2 on 2. Seems reasonable. The real part is negative, the imaginary part is positive, so we would be in this quadrant. And I can assure you that that's right. All right, so basic idea, when you're adding complex numbers or subtracting complex numbers in polar form, you actually have to convert back to Cartesian form. All right, let's keep moving. Let's look at the next thing. So the next thing is when we're multiplying by a scalar. So we've got our complex number. Here it is. And let's say we want to multiply that by a scalar, where that's some scalar k. It's an element of real positive numbers. Okay, all we're going to say is that the argument doesn't change. Now remember, the argument's basically just this angle in here. So we can scale that up, but you'll notice the principal argument of z is equal to the principal argument of k multiplied by z. So we end up in a situation where the angle doesn't change when you multiply your complex number in polar form by a scalar. Positive scalar, I should say. Okay. All right, it's a little bit trickier when we multiply by a negative scalar. So now we can see that k is negative. So we've got some complex number over here. We multiply by a negative scalar, we're getting all these values down here. So we have two situations here. So we'd say that the principal argument of k multiplied by z, where k is a negative real number. Okay, if the principal argument is between 0 and pi, so remember, the principal argument goes from negative pi around to pi. It's broken up into two parts, from 0 to pi, and then from negative pi to 0. So if the principal argument is between 0 and pi, then when you multiply by a negative scalar, the principal argument becomes the same argument but minus pi. So you can see down here is clearly a rotation of 180 degrees, which is pi radians. Okay. Similarly, if our complex number sits between negative pi and 0, so sits somewhere down here. So now just sort of thinking in reverse, if your complex number sits somewhere down here, you would need to add pi to get over here, to get to the principal argument of the new complex number. So if the angle of z is between 0 and pi radians, multiplying by a negative number flips it to the opposite side by subtracting pi radians. Similarly, if the angle of z is between negative pi and 0 radians, multiplying by a negative number also flips it to the opposite side, but this time by adding pi radians. Okay, so that's sort of the effect of multiplying by a negative value. Yeah, hopefully that's interesting. All right, next thing. What we're going to look at now is when you have two complex numbers in polar form and you want to multiply them. And this is where polar form is really useful, because if it's in Cartesian form, you have to do lots of binomial expansions and it gets a bit messy and a lot of square roots and stuff. So this is where polar form can be really useful. So sort of big picture idea here. If z1 equals r1 cis theta 1 and z2 equals r2 cis theta 2, then z1, z2 equals r1, r2 cis of theta 1 plus theta 2. Okay, in essence, if you want to multiply two complex numbers in polar form together, multiply the moduli together, so the numbers out the front, and add the angles together. So let's just run through this example here. Let's look at z1 and make sure we've got it all sorted here. So z1 has a moduli of 3. So it needs to be on this circle, the 3 circle, and has a principal argument of pi on 6, or has an argument of pi on 6. So what we're going to say is, well, this is pi on 12, 2 pi on 12, which is pi on 6. So z1 is in fact at that point. I think you would agree. Because remember, these are increments of pi on 12. Okay, z2 has a moduli of 2, so it's on this circle here, and has an argument of pi on 4. So that means it's here. It's pi on 12, 2 pi on 12, 3 pi on 12, which is pi on 4. Okay, and what this rule is saying is, if you want to find the multiplication of them, you multiply the moduli and then add the angles. So 3 times 2 gives us 6, so that gets us up here, and then add the angles. So we're getting pi on 6 plus pi on 4 gives us 5 pi on 12. So let's check that this green one is in fact correct. Pi on 12, 2 pi on 12, 3 pi on 12, 4 pi on 12, 5 pi on 12. So that does look pretty good. That's in the right spot. Okay, what we can do, I should just mention that, so the answer is 6 cis 5 pi on 12, because it's on the 6th circle. Okay, so just for fun, we can sort of play around with what happens if we change these values. You can see that when you multiply two complex numbers, it has the effect of scaling up the resultant vector. So you see how the green one's larger than the other ones combined, generally, unless we get a value between 0 and 1. Anyway, you get the idea. It has an effect of scaling up the resultant complex number, and there's obviously a rotation factor, and that rotation factor is just the addition of the two complex numbers. So you get all this kind of fun stuff happening. And yeah, that's just an example of how two complex numbers multiply. All right, the next part's a bit more tricky because we're going to look at a proof of that. So I sort of just stated the facts there, that this is how you do it, but why is that true is a much harder question. So let's look at that. Basically, we're doing here what's called a proof of the multiplication principle of complex numbers in polar form. So z1 times z2 equals r1 cis theta 1 times r2 cis theta 2. Okay, if you write the whole thing out, you'll get this. Okay, just expanding it, it's all multiplied, so r1, r2 comes out the front. Okay, expanding this binomially, so you're going to get cosine theta 1 times cosine theta 2 plus I sine, plus I sine theta 2 times cosine theta 1. I think you get the idea. You got to expand that out binomially. Okay, and then you get the imaginary parts together and the real parts together. And then you use the compound angle formulas. I'm going to put a link to another video I've made about that. But basically, the compound angle formula says sine of theta 1 plus theta 2 equals sine of theta 1 cosine theta 2 plus cosine theta 1 sine theta 2. And similarly, there's another compound angle formula, which is this one. And then, so you'll notice that this part here, cosine theta 1, cosine theta 2, this one rather, minus sine theta 1, sine theta 2, is just cosine theta 1 plus theta 2. And similarly, this part here is sine theta 1 plus sine theta 2. And so the whole thing simplifies nicely to what we proved before. Proof of the multiplication of numbers in polar form. Okay, so that's a proof of that. Okay, next thing. And I should show you this. This is just the same as what was on the previous one. When you multiply them, the green one is the resultant vector. I keep saying vector, the resultant complex number. It's just very convenient to think of them as vectors. Okay, let's keep moving. Division of complex numbers in polar form. So now, again, let's just state the rule. If you've got some complex number z1 and z2, and r2 is not equal to 0 because we can't divide by 0, basically, you divide the moduli and subtract the angles. Okay, so for example, z1 equals 6 cis pi on 3, z2 equals 2 cis pi on 6. Let's make sure they're in the right spot. z1 is at 6 pi on 3, pi on 12, 2 pi on 12, 3 pi on 12, 4 pi on 12, which is pi on 3. So z1's in the right spot. z2 is the pink one, is 2, moduli is 2, pi on 6. It's in the right spot. When we divide them, divide the moduli, so 6 divided by 2 is 3, and pi on 6. So that looks good. So let's just have a play around to see the effect of division. So we're taking the blue one, dividing by the pink one, and the green one is the resultant vector. So we're getting all this fun stuff going on. What's going on there? Oh yeah, makes sense. So that's pretty cool. All right. So that's the division of complex numbers. That's what you need to do. You're probably wondering, where on earth does that come from? And this next slide is ungodly, but let's have a look. I'm going to try and talk through it, but it's probably easier if you just pause the video and have a read through it. It just relies on a fair bit of understanding of, trigonometric identities is the hardest part. So again, I'll put links below for that, but this is probably the trickiest part here. So again, I'll just briefly talk through it. You've got two complex numbers. divide them, so write it out, fully divide them, so write it like this. Okay, rewrite the fraction, take R1 and R2 out the front. Okay, a trick you can do in maths is multiply by the conjugate of the denominator. So basically, the conjugate of the denominator is cosine theta 2 plus I sine theta 2. That's the original denominator. The conjugate is cosine theta 2 minus I sine theta 2. If you multiply top and bottom by that, you're just multiplying that whole fraction by the number 1, but you're doing it strategically. And then you use the trig identity. So if you expand this out, you get cos squared, cos of theta 2 squared plus sine of theta 2 squared. So you'll get a 1 in there. And yeah, so you get a 1. That's an exercise worth working out. I think the other ones disappear. Because remember, I squared is -1. So you get some interesting properties happening here. So all you must be left with is that, and then that cancels out. So you're left with just the number 1, which is interesting enough, I think. Okay, expanding the numerator, we do the same thing in the numerator, expand it all out. We know that I squared is -1. So this part here is +1. And so you get this. Okay, and this is, from this point, you can use the trig identities. Cos of A minus B equals cos of A, cos of B plus sine A, sine B. Similarly for sine. And so we get this. And yeah, we get that as sort of our fraction part. And then don't forget we had the R1 over R2 out the front. So you have that. And yeah, this is R1 on R2 cis of theta 1 minus theta 2. Okay, remember, so Z1 divided by Z2 is the modulus of Z1, which is just that R value. The modulus of Z2 is just R2. It's the magnitude of that. Okay, so that is our proof of division of complex numbers in polar form. Proof of, I need to change this, one sec. So that's better. Proof of polar form division theorem is what we could call that. All right, let's move on to the next part, which is what, we're coming back to this word I can't say. So proof of de Moivre's theorem using mathematical induction. So de Moivre's theorem states that for any integer n and any real number theta, r cis theta to the n equals r to the n cis n theta, where r is the modulus, and cis theta equals cosine theta plus I sine theta. We know that. Okay, so as it says here, we're doing it through proof by induction. So again, we've spoken about proof by induction before. I'll just remind you a little bit. Proof by induction just says if you can do a few steps, you can prove that it's true for all numbers. You can prove something's true. So for example, the analogy we have is if you've got a ladder going infinitely upwards, if you can get your foot on the first rung of the ladder, so prove the base case, and then take one step up, then that means you can get to every rung on the ladder. So if you can get onto the ladder to begin with, and then you can get from one rung to the next, you can get all the way up the ladder, and so you can prove it. So let's prove de Moivre's theorem. So r cis theta to the n equals r to the n cis n theta. So what we need to do is prove the base case. So we're going to say that n is 1. Okay, so if n is 1, we're going to get r cis theta to the 1 equals r to the 1 cis 1 theta, which is clearly true. Okay, r to the 1 is just r, obviously. 1 times theta is just theta. So the base case holds. So we've got our first foot on the ladder. Okay, then this is the tricky part. Or it's maybe not the next part's the tricky part, but the next part is to say is our inductive hypothesis. So assume that the theorem holds for some integer k. So assume that this is true. R cis of theta to the k equals r to the k cis of k theta. Okay, then this is the inductive step. We need to prove that the theorem holds for k plus 1, aka we can get to the next step. So we end up with this. This is what we're trying to show. We're trying to show that r cis theta to the k plus 1 equals r to the k plus 1 cis of k plus 1 theta. basically it's just saying we're taking, one sec. Yeah, sorry, we're just saying, all right, we can get to the k plus 1th term. R cis to the theta of k plus 1, so getting to the next term, is in fact equal to r to the k plus 1 cis of k plus 1 theta. That's sort of, that's what we need to show. So using the inductive hypothesis, so using this, we know that r cis theta to the k plus 1 must equal r cis theta to the k multiplied by r cis theta. And the reason that's true is just because of index laws. That k gets distributed across the first part, and then you're left with r cis theta to the power of 1 here. Okay. And then this part here uses the inductive hypothesis. So we're saying this part here, r cis theta to the k, is r to the k cis of k theta multiplied by r cis of theta. So what you're going to get here is this r is going to go here. So you're going to get r to the k r cis of k theta multiplied by cis of k theta. Okay, now this is probably the hard part that I'll put a link in to another video, not the one that I made, but one that is useful nonetheless. And full credit to the person that made that. Good job. But using the identity cis of A by cis of B equals cis of A plus B, it's not obvious at all. But you'll get this. R to the k plus 1 cis of k theta plus theta. Finding it hard to follow my own things. But yes, sorry. R to the k times r is r to the k plus 1, just using index laws. Cis of k theta plus theta is found from this, because what we're saying is we're making cis of k theta multiplied by cis of theta. Applying this identity says that this is true, k theta plus theta. So we get this. And so we have shown that the inductive step holds true. So by mathematical induction, de Moivre's theorem is proven for all positive integers n. So fun times there, huh? I feel like you can't underestimate this at all. This is how we take the powers of polar form. So for example, 2 cis pi on 4 would be 2 squared multiplied by cis of 2 multiplied by pi on 4. Like that's a powerful tool for multiplying polar form complex numbers together, because now we can do powers much more easily. Because for example, if you needed to multiply a polar number by itself multiple times, if you had to keep doing it, if you had to keep doing the multiplication process, say 6 times, if you had to multiply it by itself 6 times, and that's going to be a nightmare. So you're going to want to use de Moivre's theorem. So hopefully you found this video useful. I know it was a bit of a mouthful. Happy Pi Day. If you've got any questions, let me know. Good luck with all your studies, and I'll talk to you soon.